In this section of the course, we're going to cover the topic of logarithms and specifically derivatives of logarithms. So again, we're getting into a little bit more advanced topics, some functions that you don't see every day. The most common function generally is a polynomial. We've talked about that. We've talked about the trigonometric functions, and now we're going to get into logarithms. So let me just go ahead and explain what we're going to do here by means of a couple of examples. Just recall for me here some pretty basic integrals that we've already talked about. The integral of x squared dx, you all know what the answer to that is, and the answer to that is 1/3 x cubed plus a constant. And how did we do that? Just for review, well, we go 1 over, take the exponent, add 1 to it, write an x down, and then put the exponent again and add 1 to it. Okay? Again, just for completeness, another example, integral of x cubed dx, okay, 1/4 x to the 4th plus a constant. The mechanics of it's pretty straightforward. 1 over exponent plus 1, write x down, and then in the exponent put a plus 1 there. Now I ask you, what is the integral of x to the minus 1 dx? X to the minus 1 power. Well, if you were going to try to apply our standard old rule that we use for polynomials, then you would say, okay, 1 over exponent plus 1, and then x to the exponent plus 1. Okay, what would this equal? 1 over negative 1 plus 1 is 0, and then x to the 0. Okay, because this plus this gives me 0. Well, anything to the 0 power is 1. What does this part mean? 1 over 0. What does that mean? Well, in other math classes that you may have had, you might have learned that anything over 0 is undefined. Well, when you start to get into calculus and start talking about limits and things like that, you're going to start to realize, and you're going to have to know, that when something's divided by 0, it's really infinity. In other words, 0 can go into any number an infinite number of times, right? You can divide nothing into something a whole bunch of times, an infinite number of times. So clearly, if you were to do this, the answer would be infinity for any time that you were trying to do this integration, and this just isn't true. Okay, so this formula, this mechanical means that we use, it doesn't work when you're trying to take the integral of x to the minus 1. So that's why early on when I said the integral of x to the n dx is equal to 1 over n plus 1 x to the n plus 1. We said that was it, but we said that's only true when x is not equal to negative 1, when you don't have a negative 1 up here. This is precisely why. You can't do this integral when you have a minus 1 up here, because if you go ahead and you try to apply it, you're just going to get some nonsense answer. And this is definitely not true. So you can't do that. So what you need to keep in mind is that when you have x to the minus 1 here, this isn't going to work at all. So what we're going to do is we're going to do some definitions. The calculus book is going to give you the details, but I'm not going to give you the details here. I'm going to give you the results, and we're going to use those results. I'm going to write the properties down over here, and we're going to use them. The integral of 1 over x dx, and don't forget 1 over x is just simply x to the minus 1. The same problem we were just working a minute ago, is defined by definition to be the natural logarithm of x. And of course you have a constant, just like you do for any derivative. For any integral. So this is something you need to remember. Remember this, okay? It's something that you're going to need to work with on your test. And this just is simply done this way because when you try to apply that polynomial formula for x to the minus 1, it just doesn't work out. You get some nonsense answer. And you can go and you can look in your calculus book and figure out why this is equal to the natural logarithm of x. I don't see that as my job here. I see my job is to teach you how to work problems. But this is the result. This is what you need to remember. Now, because of this, as a direct result of this, you can also say that the derivative with respect to x of the natural logarithm of x is just simply equal to 1 over x, like this. Okay, so these two things I'm going to put over here on the side, and these two things we're going to use in this section over and over and over again, and you're going to use them in your class over and over again. Now I've got a couple of asterisks here, but I'm going to go ahead and erase those for now, just so no one gets confused, and so that we all know that this is what we need to know here. And just convince yourself that this is true. Because the integral of this is this, that means the derivative of this must be this, and that's the only thing we're writing down here. So what it tells you is anytime you come across the integral of 1 over x, you know what the answer is, and anytime you come across the derivative of the natural logarithm, you get 1 over x. And you can go and look in your book, if you're not sure what the natural logarithm is or how it's defined or what it means, you can go back and look at a pre-calculus book, or you can look at my video in pre-calculus, and we'll work a bunch of problems and actually describe what the natural logarithm represents. But it's just another graph, it's just another function defined in terms of the logarithm with a base e. So let's go ahead and work some problems. What if you were given f of x is equal to x to the 1/2 power, in other words, the square root of x, times the natural logarithm of x, and this is your function, okay? And they say, well, give me the derivative, f prime of x, okay? And you're going to have to find that derivative. Well, the first thing you should notice is that you have a function of x times a function of x, so you're going to have to use that multiplication rule. First term times the derivative of the second term plus the second term times the derivative of the first term. So let's do that. You have the first term, x to the 1/2, times the derivative of the second term. The derivative of this is just simply 1 over x. Right? First times the derivative of the second plus the second term. Okay? I'm going to go ahead and put brackets around everything so that we're very clear. The second term times the derivative of the first term. We know how to do this. We've been doing this all day. This is just 1/2 x to the negative 1/2. 1/2 comes down, x, and then you just subtract 1 off of the exponent here. So essentially this is the answer, and you just need to go ahead and simplify that, right? So what you're going to have is, you're going to have x to the 1/2 over x, which would be this part here, you just multiply these two things together, plus natural log of x over here, over 2 times x to the 1/2. And all I did was I left this on the top. This 2 is, of course, on the bottom because you're multiplying them together. And this x to the negative 1/2 just goes down to the bottom, downstairs, and you make it a positive term there. So what you're going to have here, if you simplify this, is when you simplify this guy right here, you're going to have 1 over x to the 1/2, because basically I can take out a 1/2 from there, and I'll have a 1/2 left over in the bottom. And then over here you have the natural log of x over 2 times x to the 1/2. Now this is basically the answer, and you could circle that as your answer, but if you wanted to tidy things up just a little bit, then you could try to get a common denominator here, and the simplest way you could get a common denominator is just to multiply this fraction by 2 over 2, which of course is just 1, so I haven't changed anything. So what you would get is 2 over 2 times x to the 1/2 plus natural log of x over 2x to the 1/2. Okay, now I have a common denominator, and then I can just write 2 plus natural log of x over 2 times x to the 1/2. And then that would be my answer. So you see, it's the same old story as before. You're taking a derivative using that multiplication rule for derivatives, but now you have a couple of additional tools in your box to actually evaluate that derivative of the natural logarithm, which is really what the problem's about. So we're going to work a few more problems of increasing complexity with the derivatives here in the integrals, and hopefully we'll get it all squared away in the end. What if you had a function like this, natural log of, and then inside here you had x to the 1/2, which is just the square root of x, and you wanted to find the derivative here? Well, you're going to have to use the chain rule, because I've given you what the derivative of x is equal to, but here you have the derivative of the natural log of x, but here you have the natural log of x to the 1/2, so it's not quite the same. So what you do is you take the derivative of the big picture and then multiply by the derivative of the inside, which is what we've been doing all day. So the derivative of the big picture is just going to be 1 over x to the 1/2 because it would be 1 over x if it were just natural log of x, but since it's kind of different on the inside, I just put that in the bottom, and it looks kind of like this. But you can't stop there, because now you have to multiply by the derivative of the inside. And you know how to do that, 1/2 x to the negative 1/2, right? We've been doing that all day. And so in the end, what you're going to have is 1 over x to the 1/2, this is this one. You're going to have a 2 out here in the front because you've got this 2 from here. And then I'm going to move this one downstairs. I'm going to have x to the 1/2 here. So then in the end, you're going to have 1 over 2. And then here, these are multiplied together, so you can add the exponents. So you're just going to have 2x. So then the f prime of x would be 1 over 2x. Because when you multiply these two exponents together, then you can just add their exponents. So you just have to know, you see there's not many steps in the problem, it's just knowing the order in which to do everything. And how do you get that experience? Well, you get that experience by working problems. It's really the only way you can get this experience. So we'll go into a problem that's a little bit, I guess, more complicated. What if you had h, which is some function, is equal to the natural logarithm of y cubed times the sine of y. And this is all inside of the natural logarithm, and you want to find this derivative. So how do you do that? Well, again, you take the derivative of the big picture and you just keep multiplying by the derivative of the inside. The big picture is, the outside function here is the natural logarithm, so what you're going to have is 1 over y cubed times the sine of y. That's the big picture, but then you've got to multiply by the derivative of the inside. So I'm going to write it like this, and I'm going to put a big derivative symbol here. So big picture is it's 1 over this argument, because that's the outside function, times the derivative of whatever's in the inside. Okay? So then when you do this, you're going to get, what's the derivative of this quantity here? This is two terms multiplied together. So you have the first term times the derivative of the second term. Derivative of sine is cosine, plus the second term times the derivative of the first term, which is just 3y squared. And we've been doing derivatives of that type all day long. So, in the end, to tidy things up a little bit, what we can do is we can pull out, you see we've got a y cubed here and we've got a y squared here, and I can pull out a y squared. So over here I'm going to pull out a y squared. On the bottom I'm going to have the same thing, y cubed times sine of y. And then I'm going to tidy things up on the inside. I'm going to have y times cosine of y plus 3 times the sine of y. All I did was pull out a y here, and so then y squared times y gives me y cubed, y squared times this term gives me this y squared, and everything else in the inside is really the same. And why did I do that, you might ask? Well, because when I do that, I can cancel this y squared with that y squared on the bottom. And so in the end, what I'll have is 1 over y times the sine of y times y cosine of y plus 3 times the sine of y. Okay? You know, and you can continue simplifying this until you're blue in the face, but this is basically the answer. You know, you could multiply this term in here, and you can multiply this term in here, and it will get a little bit simpler. But essentially, this is the answer. This is the mechanism that you're after to get the answer. And like I say, there's different levels of simplification that you can go through if you want. I mean, we could have easily multiplied those terms out. We would have got a cotangent somewhere, and we would have had some signs that would have canceled and all that business, but that's more of just the mechanics of the algebra more than anything else. Okay, now let's do something that kind of combines what we learned in the last section with what we're learning in this section. Let's say you have e to the x times the natural logarithm of x, and you want to take the derivative. Well, you have a term in x and a term in x, so you have to use that multiplication rule. So, and I'm hoping that you guys are able to kind of remember this a little bit now. It's the first term times the derivative of the second term. In this case, that's just going to be 1 over x, because this derivative of natural log is 1 over x, plus the second term times the derivative of the first term. Now, you remember that e to the x is the indestructible function, so the derivative of e to the x is just simply e to the x. So in the end, what you're going to have is e to the x. I'm going to factor in e to the x out, and you'll have on the inside a 1 over x plus natural log of x. Okay, and that's it. You see, it's just the mechanics of knowing how to do the derivatives and just knowing a couple of derivatives in your pocket, and you're able to take derivatives of some fairly complicated functions, really. If you tried to look at them, you'd see that they were, by and large, fairly complicated. Now let's switch over to doing a few integrals. What if I had an integral from the limit of 4 to 8 of 1 over x dx? We'll start out with something pretty easy. We know what this integral is equal to. It's equal to the natural logarithm of x. Okay, so we've done the integration, and we're going to evaluate it from 4 to 8, okay, like that. This vertical bar reminds me that I still need to evaluate this integral here, and then using that fundamental theorem of calculus, you'll have the natural log of 8 minus the natural log of 4. So you evaluate it at the top, and you subtract evaluating at the bottom, and that's what it's equal to. And then if you remember back from your properties of logarithms, which probably was covered in an Algebra 2 class or a pre-calculus class, anytime you have two logs that are subtracted, that's the same thing as the log of the two things divided by each other. So when you have log of something minus log of something, that's the same as the log of the first thing divided by the second thing. And it doesn't matter what base you're talking about, it's true for any logarithm with any base. So then this just reduces to the natural log of 2. Pretty basic problem. You're not going to have a problem that easy on your test, but I think it helps you figure out what to do with some of this stuff. Okay, let's switch to something a little bit more challenging. What if I had the integral of 1 to e of x squared plus x plus 1 over x dx? Well, anytime I see a polynomial divided by a single term, I think to myself that I can split these terms up into different integrals. Okay, so what I'm going to do is, that's exactly what I'm going to do in the next line. I'm going to say, okay, this is integral from 1 to e, and what I'm going to have is x squared over x plus x over x plus 1 over x dx. And I wrote it like this so that you could clearly see what I'm doing here. You just, if you look at it in the backwards sense, all these fractions have the same common denominator, so you can add them up. And so on the top you'd add them up, which is what you have here, and the bottom would just remain the same. So then to actually pull off this integration, you're going to have one integral of 1 to the e, from 1 to e, and you're going to have the integral of x, that's this term here, plus 1 over x dx. Okay? So now you have three terms. I know how to integrate this, I know how to integrate this, and now that I've learned this, I know how to integrate that. So let's pull that off. Integral of x, using that polynomial rule, is just 1/2 x squared. We've done problems like that before. Integral of 1 is just simply x. We've done many problems like that before, and now we know that the integral of 1 over x is simply the natural logarithm of x. Now we've done plenty of problems like this. And don't forget that now that we've done the integration, we need to pull off this integration from the two limits from 1 to e. Okay? So let's go ahead and do that. For the first term, we're going to plug in this whole thing at the value of e. So we're going to have 1/2 e squared plus e plus natural log of e. Okay? And then we're going to subtract off the second term, which is going to be this whole thing evaluated at 1. So we're going to have 1/2, 1 squared just gives me 1, plus 1 plugged in here, plus natural log of 1, like this. Okay? So let's just go ahead and bust it all out. So what we're going to have is, we're going to have 1/2 e squared plus e. Now what's the natural log of e? Okay, the natural log of e, okay, how do you find this out? Remember, this is base e. Anytime you have a natural log, it's a log to the, with a base e. So the way you figure this out is e, the base, to what power would give me what I'm taking the log of. And of course, since you've written it like this, you know that you've got to be talking about the power of 1. E to the power of 1 will give me e. You could also put it in your calculator and figure out that the natural log of e is 1. That's what I'm trying to tell you here. Over here, you have minus 1/2 distributing in this negative, minus 1, again distributing in the negative, and then minus the natural log of 1. But again, let's think about what is the natural log of 1. The natural log of 1, it's a base e, don't forget. So then you say, okay, base to the what power will give me 1. Base to the what power will give me 1. And anything to the 0 power will give me 1, so this must be 0. Okay? You see? So now things are becoming a little bit simpler. This 1 is going to cancel with this negative 1. And then I've got a 0 hanging out here. So at the end of the day, I'm going to have 1/2 e squared plus e minus 1/2. And that's the answer. So this is a definite integral over 2 points of some weird-looking polynomial function. It just so happens that when I split it up, I need to use this logarithm because the integral of this term is a logarithm. And when I do that, it just becomes a regular old integral at this point. And you know, I just need to know some properties of logarithms. So if you're having trouble figuring out, you know, what's the natural log of 1, what's the natural log of e, and stuff like this, you know, go review your properties of logs, natural logs, or you can get my video on pre-calculus and it covers all that stuff in there. Just do a couple more problems, integral problems. What if we have the integral of x plus 1 over x squared plus 2x dx? Okay? Well, first thing that we can do is we can try to use substitution just like we always try to do initially. And so what I'm going to do is I'm going to choose the bottom to be u and just see what happens. If it doesn't work out, well, it doesn't work out. Du dx is just going to be 2x plus 2. The derivative of this term here, this is 2x plus 2. So then du is equal to 2x plus 2 times dx. And so solving for dx the same way we always do in these problems is 1 over 2x plus 2 times du. Okay? So when we plug this in here, what we'll have is we'll have the integral of x plus 1 over u, obviously, because u is equal to this, times dx. But dx I've already defined as 1 over 2x plus 2, and then we have the du left over here. Now, this is starting to look really nice because you see what I can do is I can write it like this. I can factor out a 2 here and make it like this. You see, I just factored out a 2 here, and so now I have an x plus 1 and an x plus 1, which, as we said before in substitution, you really want to see a cancellation. If you've started to cancel something, then you've probably done something really good. I'm going to take this 1/2, I'm going to pull it out of the integral, and then what you're left with on the inside is just 1 over u du, which we know now is just the natural log of u plus a constant, obviously, because there's no definite limits to the integration here. We don't want to leave our answer in terms of u, so we just want to go ahead and plug in x squared plus 2x plus a constant.